Good afternoon. My name is Jaap Jansen, and I would like to thank the organizer, Zhang Lu, for inviting me to tell you something about IVIM perfusion techniques. And I'd like to also apologize for the fact that I'm not physically present due to some logistics reason. I have no financial interest or relationships to disclose. So, in order to start, we travel back in time approximately 35 years ago. This was the first application of diffusion MRI in the brain. Denis Le Bihan published in two papers the concept of intravoxel incoherent motion MR imaging in 86 and 88 in radiology. And he actually um, basically also introduced diffusion MRI. And he showed some images. On the left, you see a T2 weighted image of a 5-year-old child with chronic ischemia, and on the right, which Le Bihan designated the IVIM image, but nowadays we would call it the ADC image, apparent diffusion coefficient image. You see some darker regions, and he thought back then this was due to a lower perfusion, but yeah, I'm not so sure about that right now. But anyway, so in '86 we had the first diffusion images. So what is IVIM, or intravoxel incoherent motion? It's a technique that's based on diffusion, so it's a diffusion weighted MR technique. It's sensitive for the diffusion properties of water, and it has been coined to measure diffusion and pseudo perfusion locally and quantitatively. And the idea is that you can obtain signal from the parenchyma, the slow-moving compartment, and signal from the microvascular blood, which is the fast-moving compartment. So diffusion MRI can be measured using the Stejskal-Tanner Sequence, which was introduced in '65, and it's basically a regular spin echo sequence with a 90-degree and a 180-degree pulse, uh, and some additional gradients that are sensitive to diffusion. And the strength of the diffusion weighting is designated by the B value, and the B uh, can be calculated from several settings of your gradient, so the duration, the amplitude, and the timing. And the fact that it's called B is because Le Bihan used his own name, so the B comes from Bihan. And it's good to know that with IVIM we acquire MRI images with uh, several different B values. And if you look at the top here, you see we plot the signal, the logarithmic of the signal as function of B value. Then you can see that there is a strong decay, and later on we'll also dive in a little bit more deeply into the shape of the association. Um, Although it was originally coined in '86, IVIM has not been very popular until the beginning of this century, when there was truly a rise in popularity. And we think that it's due to improved hardware that made the measurement more sensitive, which basically also caused this renewed interest, because it has some fascinating possibilities to look at. So if we look at the origin of the IVIM signal, we can see that it's of course based on diffusion weighting, and we're looking at incoherent motion of water, and there's two pools that are assumed to exist. One, the incoherent motion is due to thermal energy, so that's the Gaussian movement of the water molecules, mostly in the parenchyma. and there is the signal from the blood flow circulation in the microvasculature, which is assumed to be pseudo-random. Hence, this part has been coined pseudo-diffusion, but also perfusion. And if we then go to the traditional model to analyze IVIM, we use a two-compartment diffusion model. Here you can see the two compartments. In red, we have the microvasculature, which is the pseudo-random capillary network, and in blue we have the water molecules in the parenchyma, which basically have Brownian motion. And so there's two terms in your formula, and D is the diffusion parameter for the parenchyma, and D star is the pseudo-diffusion. So we end up with three parameters. We have a perfusion volume fraction, which is basically the fraction of these two compartments. We have the parenchymal diffusion and the intravascular diffusivity. And in order to analyze this, it is common to use a two-step approach. So here you see this graph again, where the signal, the logarithmic signal, is plotted as function of B value. So in this case, we fit the B values of 200 and higher to a mono exponential. Using that, we estimate the D, so the diffusion coefficient of the parenchyma. And later, we fit the full curve with the bi-exponential fit, which provide us with the F and the D star. And this is a relatively robust way to fit IVIM data. It's kind of coming the standard nowadays. So one of the very important questions that was raised early on, so in this case in the 90s, 1990, by Hunkelman, was whether IVIM truly measures classical perfusion. So we know that IVIM is sensitive to motion of blood. This fast decaying component is assumed to be the perfusion fraction. But how does that compare to what is known about classical perfusion? Usually when we talk about perfusion, we talk about the delivery of oxygen and nutrition to cells through the capillary network. And you model the uptake and washout of tracers. So traditionally you use the nuclear medicine techniques, but of course ASL is also very popular. And with ASL you measure the transfer of blood labeled outside of a certain region of interest, and you see how it arrives at that region of interest. And all these classical perfusion techniques end up with a measure of blood flow, which can be expressed as milliliters per minute per 100 gram of tissue. And is that also possible for IVIM? So based on this comment from Henkelman, Le Bihan wrote a response in '92, and there he introduced his visions around the capillary network, so in which he tries to bridge the IVIM to the classical perfusion techniques. So what he does, he assumes a certain orientation of the blood vessels, and then hence you have a certain capillary network geometry, and he defined some aspects, so the capillary segment length, the total capillary length, and the visible water content fraction. And there he derived this formula where cerebral blood flow is related to the visible water content fraction and the capillary length times F times D star. So F is the perfusion fraction and D the pseudo diffusion, and hence he claims to have yeah, CBF as we know it from the classical perfusion techniques. But it's very good to realize this is only valid under certain assumptions, and it remains to be seen if this is always the case. So I'm also happy to share some work from the group from Thijs van Os and Leiden, who assessed the validity of the IVIM model. We know basically that although it is assumed in the bioexponential model that the D to D star decay is monoexponential, in fact it is not, because if you look at the water in the blood flowing through this capillary network, that there's a distribution of velocities, not just one single velocity, and this pseudo-random orientation of the capillary network is not entirely random, which makes the D star decay a little bit more complex. Then there's some other information that indicates that it's not entirely classical perfusion, because if you look at the CBF value acquired through IVIM and then look at the ratio of gray matter over white matter, you see that there's a 20% increase of cerebral blood flow in the gray matter compared to the white matter, whereas from the classical perfusion experiments like dynamic susceptibility contrast MRI or oxygen PET ASL, we know this ratio should be like 2 to 4. So there's some discrepancy there. So therefore, maybe the model is too simplistic. In order to investigate this a little bit better, the group from Thijs van Os created the ASL IVIM technique, in which an IVIM aspect, a readout gradient, was attached to an ASL sequence, and by combining these two sequences, it was possible to obtain IVIM signal from the arterial blood flow at different aspects of the vascular tree. So after running their experiments, they found that this vascular signal of the conventional D star has more complicated diffusion properties than is generally assumed in the standard IVIM model, and hence requires more research to better visualize what is actually the signal what we measure with IVIM. Nevertheless, IVIM, although it's still unclear what the precise underpinnings are, has already been applied in several clinical examples. And if you then look at this list, you see several applications from oncology in several organs: liver, breast, head and neck, pancreas, kidney, and prostate. And I'm especially interested in the brain, so I will highlight some cases in the brain. And if you're interested in any of these other organs, I would highly recommend to read this book that was edited by Denis Libihan about IVIM. In these images, we see the example of a right-sided middle cerebral artery infarct, and on the T2 you see a nice hyper-intense intensity, on the ADC map a hypo-intense intensity, and if you then go to the perfusion on the ASL, there's clearly hypoperfusion in this region, and if you go to the F, so the perfusion fraction of the IVIM, you also see a lower value there, which also is indicative of lower perfusion. Although a little bit more frontally here you see still some signal, which could be due to collateral flow. On this slide there are some other images from Christian Federer, where he applied IVIM and other techniques in a patient with glioma. On the top you can see a grade 4 tumor, on the bottom a grade 2, and we can see on the T2 the tumor is relatively big. You see clearly that there's contrast uptake after gadolinium administration, and there's also an increase in perfusion if you look at the traditional DSC, CBV, but also if you look at the F from IVIM. On the bottom you have this low-grade tumor. You can already see that there's hardly any uptake with gadolinium, and there's also no increase in perfusion. Opposite, it seems like to be a decrease in perfusion, both on the IVIM and DSC images. On this slide, we see some images from a patient with the Oligoastrocytoma, again from Christian Federer. It's a grade 2, and we start on the top. This is 2 years after the resection, which was incomplete. You see a hyperintense signal on the T2 weighted. On the T1 plus gadolinium, so post-contrast, there's no signal increase, there's no leakage. However, if you look at the DSC, you can see there's a decrease of perfusion, and on the F, you also see a lower value for the perfusion fraction. This patient was scanned again after 8 months, and then after 8 months, the T2 hyperintensity is extended frontally, and you now also see on the post-gadolinium scan some uptake, which indicates that there is some new tumor tissue. And if you then look at the perfusion measures on the DSC, you don't really see a clear difference between the baseline scan, but on the F scan you see a increase in signal. And the idea is that in low-grade tumors with a high perfusion, it's usually a bad sign of prognosis, and it's also called the angiogenic switch, which mainly means that new tumor tissue is growing and causing this bad prognosis. On this slide, we have some images from a patient with a meningioma, images from Togao et al. Meningioma is an extra axial tumor, and you see this big mass on the T2, and you also see some signal increase on post-gadolinium scan. And if you then look at the typical vascular IVIM measures, F, D star, and F times D star, you can see an increase in all these values, which hints at an increased perfusion in this region, which makes sense in this type of tumor. After showing these clinical cases, I would like to discuss the merits of IVIM. It's a nice technique that can provide information out both about the white matter and the gray matter. There's a relatively high signal-to-noise ratio. It does not require any contrast agent administration or labeling, so label efficiency is not an issue. And it can measure interesting properties of blood flow and proton motion. Some people call it perfusion, but that takes me to the take-home message. I think we can all agree that IVIM does not measure classical perfusion. However, it is sensitive to the vasculature and processes that are related to changes in vasculature. Therefore, it can provide clinically relevant contrast. However, it requires more research to understand what is the precise mechanism that underlies the signals. And by that, I would like to end my presentation, and I'd like to thank you for your attention. And If you have any questions, I will be available hopefully later for a Q&A, and you can always send me an email. Thank you.